You may wonder why I've gathered you here today. Well, it's about the infidel. This is the inline filament diameter estimator, low cost, short, the infidel. So this is a sensor that is designed to go into the filament path on your 3D printer. So basically you attach it right before the filament enters the extruder, and the idea is that the firmware can then compensate for any differences in filament diameter and filament cross-sectional area essentially by adjusting the extrusion multiplier. That's something that not all firmwares support fully yet. But it is a bit of a chicken and egg problem where, if you don't have any sensors available, then, why would the firmware support it? So this is my attempt to provide a low-cost, accessible sensor to measure that diameter. And I know that it is precise enough to give you readings that are very usable because I did use it in the filament spool measuring device that we saw in the last video. So today I want to show you what components go into this, how it's assembled, how it evolved from the older design that I did in 2015-ish, and what it has to do with this filament extruder. But first, a word from our sponsor, Morning Brew. Morning Brew is a free email newsletter with actual news on tech, finance, and business. It's 5 minutes of reading up on what's important, written in a way that already puts you in a good mood for the day. The newsletter comes out every Monday to Saturday, and if you're in the US, they send it out at the perfect time to have your morning coffee with. But since my time zone is 6 hours ahead of Eastern time, it also totally works for getting up to speed during lunch, instead of spending that time doom scrolling through social media. Did you know that in the US alone, there are already over 1.7 million registered drones, plus however many unregistered ones? Just imagine the noise all those would make if they were up in the air at the same time. Also, there's been an increase in toy sales by 16% recently. I'm not a toy economy expert, but little info bits like these just get you thinking about all the unexpected effects of the strange times we live in. So if you're interested in business, finance, or tech, sign up to Morning Brew. It takes 15 seconds, it's free, so check out the link in the description. Thanks, Morning Brew. Okay, so let's actually start with this sensor that was designed for this filament extruder that I built in like 2013, 2014. It made some filament, but it wasn't very good. By the way, if this is interesting to you and you'd like me, cover it in more detail in video, just let me know in the comments below. But this essentially is the original sensor that started it all. So it is a mechanical lever, that's like the main part. The filament goes, in this way, out this way, and it rolls between these two bearings. Down here there is a magnet embedded in the lever, and that moves to and away from a Hall effect sensor, an analog linear Hall effect sensor that measures how strong that magnetic field is. So the idea is the larger the filament diameter, the closer this magnet is to the sensor, and the stronger the magnetic field is going to be that this guy picks up. So this was a good proof of concept, and this actually worked pretty well. It was pretty large and bulky, and it was only pre-tensioned by gravity really, so the only weight on the filament is the weight of this bearing, because it was straight out of an extruder and it didn't want to squish the still hot filament into an oval shape. Now if you're using this as an inline sensor, that kind of doesn't matter anymore, so I've redesigned it twice now to be a more compact, a more reliable, and a very cost-effective solution to use as a filament sensor. So this entire thing built with a custom PCB costs about $5. The goal for this one was under $10, which obviously we achieved, but at volume you could probably make this for $3 or $4. Definitely, if you source it yourself, under $10 is very much feasible. So this is where we are at today. So you can see this has been quite an evolution in designs, which is what I love about 3D printing. You can just, design something, print it, make a few changes based on what you're seeing and print it again. And, you end up with something that is very usable eventually. So let's check out how this one was built with the newest design iteration, and maybe that's going to give you a better view of how this thing actually works. The assembly begins with the block itself. It receives a few threaded inserts that very smoothly slide into the printed cavities for them. Next, we can glue the Hall effect sensor into position. I'm using a thicker CA glue for this, which sets up very fast, which allows for some gap filling between the sensor body and the printed block. Next, the idler bearing gets inserted and secured in place with the 18mm dowel pin. The CA glue for the Hall effect sensor should have hardened by now, so we can attach the PCB, sliding the legs of the Hall effect sensor through the PCB's holes from the back. Then the legs of the Hall effect sensor can be soldered in. Next, the magnet. This is a 6x2mm N35 neodymium magnet, and it needs to be installed in the orientation where the LED on the board does not line up when the magnet touches the sensor. I've already flashed a firmware to this board, and I'm temporarily powering it through the programmer. The lever then receives the remaining 3 bearings, with the roller bearing going into the center and being fixed with a 16mm long pin and 2 more 623 bearings on the hinge that will allow this lever to smoothly rotate up and down. Then the lever can be inserted into the block and fixed in place with a 24mm pin. The lever still needs to be spring loaded so that it actually presses against the filament. For this, we're going to use a spring from a ballpoint pen, as well as these printed slugs to help the spring center in the bore. The spring is then pre-tensioned with this scrub screw. This is also used to adjust the pre-tension on the lever, because not every ballpoint pen has the same hardness spring in it. And there it is! A standard 4x2mm Bowden tube can be inserted into either end to help guide the filament and to tie it into your extruder setup. So the basic way that these work, this is one that I made in I think 2015, this is one that I made last week, is you still have that same idea. You have a bearing, a roller bearing that moves a lever up and down with a magnet that moves to and away from a sensor. And instead of being, hooked into a main Arduino to read out that sensor, this is now converting the analog readings from that linear Hall effect sensor into a calibrated diameter reading directly on the sensor, so that, whatever firmware this attaches to just needs to worry about what to do with that reading and doesn't have to deal with the how do I get to that reading stage. So this sensor is still built with the exact same SS495A linear Hall effect sensor. This is a fairly expensive one. This one is $2 from a German reseller. I just bought a 10-pack of cheap ones for 50 cents each. That goes straight into an Atiny 85. That does the entire mapping, interpolation, filtering. So basically, you calibrate this by inserting 3 different drill bit sizes, 1.5, 1.7, and 2mm. And then there's a lookup table, actually based on the thermistor code from Sprinter, that interpolates the readings it's getting from the sensor onto those calibrated diameters it knows about. Now, this mechanism is not super linear, but because we're calibrating 3 diameters here, it should be very close to what the actual, inserted filament probe is going to be in diameter. It should be fairly accurate. So there's a button on here for calibration. You press that, insert the drill bit shaft, press it again, insert the next size up, and so on. That's not implemented in firmware yet, but the firmware is 20 lines, 30 lines. The Atiny does all the analog reading, all the logic, and then it spits it out either through I2C, which is not a great bus for doing like long wire runs, but for DIY applications like these, it does work. It does work well on the filament spool measuring device with 3 sensors connected. So I don't think it would be much of a problem to do it on a 3D printer. This one does I2C for now. I know that RS485 or CAN bus are better, but they are more expensive and they add more component overhead. And like I said, this is supposed to be a very low cost first step. The other option for outputting a filament diameter, which Marlin actually supports today, is through an analog voltage. So and this is basically just a low pass filter on the PWM output, and the Atiny can then basically output an analog voltage where 1 volt, where 1 volt is 1 millimeter of diameter. So a 1.75 millimeter filament would output 1.75 volts. So cost-wise, this sensor, like I said, is less than $5, and the most expensive part is the custom PCB. I paid about $4.50 for this populated PCB. However, that was including express shipping. So if you have just regular sane shipping and maybe make them at a higher volume, then this is going to be a bit cheaper. However, you don't actually have to use, this proprietary PCB. You can use an Arduino Nano, an Arduino Pro Mini, a Pro Micro, anything that, can read an analog input and output it over whatever interface you want, which is really any Arduino or even any other microcontroller. Even an ESP8266 could do that job. So for this design iteration, I went with the Attiny 85, which is basically the cheapest Atmega or Atmel chip that does what I needed to do, but it's still Arduino compatible. So pretty much everyone will be able to program it, and the ISP interface is the same as for any other Atmega chip. This is an Attiny, but it's the same thing basically. So a couple of improvements of this iteration versus the one that I was using on the Filament spool diameter measurement rig. This now uses dowel pins versus screws for the bearings to ride on. That just makes them a bit better, constrained to where they're supposed to be. Again, this is all pre-tensioned. There is a ballpoint spring and a grub screw in here that kind of keeps this lever under pressure, so any slop in the bearings should be taken up. But just for good measure, dowel pins, they're really cheap too. We're now using threaded inserts on the entire thing, so on the bottom where the sensor is mounted, as well as on the positions where the PCB is mounted. The mechanical design has seen a few really minor tweaks. For example, the filament path is now constrained tighter against the idler bearing, so that filament that is a bit wobbly and has a few kinks in it doesn't move the lever up and down anymore as much. But the goal for this was still to keep it printable and to, enable everyone to make this without any real special equipment. And I think this sensor is exactly that. And again, it's supposed to be a starting point that, you can base a sensor design off of, or just to enable firmwares to support some sort of a sensor. So this is, as I originally announced, this is fully open source. This is public domain, no rights reserved. It's up right now on Pusher printers and Umagine. So that is the mechanical design, the PCB design, and the firmware that's running on here. Some of the files are a bit of a mess, but I thought, well, better put it out there now before I go into the endless loop of trying to improve it, and then it never gets released. So you can use that in any way, shape, or form that you want. If a 3D printer manufacturer comes along and implements something based on this in their printer, be my guest. I just care about 3D printers becoming better tools over time. One possible improvement that I could think of is to use these V623 bearings instead of the straight 623 bearing for the idler, so that oval filament is actually touching on 3 points and not just on 2 points where it's being clamped down essentially. This I don't think is super necessary. We've seen in the filament measurement video that filament really isn't all that oval. Maybe cheaper filament is, but the ones I've seen don't have a significant issue with being unround, essentially. And of course, what still needs to be improved is the firmware that's running on this Attiny. This really is just a first iteration to get it out, to get it functional, and to have something, as reference, as, a starting point, really. So, like I said, if you're interested in making one, the design files are all linked below. They're free to download, free to use, free everything. Yeah, I hope you got something interesting out of this. I hope you found this helpful. Maybe you find the sensor helpful. Get subscribed if you want to see more designs and kind of 3D printer improvements like this in the future. Support the channel if you think that's worth something. Keep on making, and I will see you in the next one. Bye!